space. Yeah, but how do you define it? What's its definition? Number of vectors in the basis. Span of the basis? No. That's the whole vector space, not its dimension. Yeah. Nope. N is not a good answer. No. Yeah, but what the heck is N? Nope, I'm looking for number of vectors in the basis. True or false? If the dimension of V is N, then any linearly independent set of N vectors in V is a basis for V. True. That's a really important theorem from 4.5. And true or false, the dimension of the null space of A is the number of free variables in the equation AX equals 0. True. And what is the dimension of the column space of A? As a follow-up, how do you find the dimension of the column space of a matrix? Number of pivots. Number of pivot columns, yeah. Okay, so we're going to talk about dimension today. One important property of a vector space is its dimension. So when we talk about R2, R3, R4, those numbers we call the dimension, right? But we can expand that number to apply to any vector space, not just Rn. Okay, so we're going to learn the definition of dimension and discover an important theorem about how to use the dimension of a space to build a basis for the space. All right, so the two most important things in this section were the definition of dimension. I have it the first thing in bold here. It says if V is spanned by a finite set, then V is said to be finite dimensional, and the dimension of V is the number of vectors in a basis for V, regardless of the choice of basis, right? The basis will always have the same number of vectors, and that number is called the dimension. And the basis theorem says that if you have any p-dimensional vector space, so we have some vector space, its dimension is p, any linearly independent set of exactly p elements is automatically a basis for V. And also, any set of p elements that spans V is automatically a basis. So normally, to prove something's a basis, you have to show that it spans the vector space and that it's linearly independent. This theorem says that if you have exactly p vectors in a p-dimensional vector space, you only have to show one of those two things, and you've shown that it's a basis. You can show that it's linearly independent or that it spans the space. Usually showing linear independence is easier than showing spanning. And then the dimension of the null space is the number of free variables in the equation AX equals 0, and the dimension of the column space is the number of pivot columns in A. Okay, so let's look at a couple of vector spaces. I want to find a basis for each vector space and then state the dimension of the vector space. So I need to come up with some linearly independent vectors whose span is that guy. Say it again. 2, 0, 1, 0. Okay, can you explain how you came up with those vectors? Yeah, so you kind of like pulled this apart. So if you put an A on this first vector and a B on this guy and a C on this guy and added them all up, you would get that vector. So I have these three vectors. Are they linearly independent? Yeah, none can be a multiple of the other because they all have zeros in different positions. Well, no, yeah, this guy's a 0, 0, 0. Yeah, what about the D? I guess I need another one. Thank you. Thank you. So I've got 4 vectors. Linearly independent. Do they span the, we know that they span the vector space because that's how we picked the vectors, right? If you take linear combinations of those, you get the vector space V. So if we can show that these are linearly independent, we know that it's a basis. How would I check that they're linearly independent? If I wasn't sure by inspection, how would I check? I would row reduce it, and what would I be looking for? Pivot in every column. Yep. Row reduce. Pivot in every column tells me that it's linearly independent, right? So I think, like, I can tell because when I see a 0 here, 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 and here, there's no way you could take a multiple of any of these and create that 0, right? So none of these could be a linear combination of the others by inspection. But if that's not obvious, you can always row reduce and look for pivots. Okay, so what's the dimension of this vector space? 4. Yeah, because this is a basis. It's a linearly independent spanning set. It's a basis. There are 4 vectors in it, so the dimension of V is 4. Yep, the dimension is the number of vectors in the basis. All right, what about the vector, all the vectors that look like A, B, C, D, such that A plus B minus D equals 0? Yeah, let's look at A plus B minus D equals 0. What do you get if you solve that thing for A? Yeah. Okay, so instead of an A here, I could instead write W as the set of all vectors that look like negative B plus D, B, C, D. Does that make sense? Such that B, C, and D are in R. Oops. Is that easier to write a spanning set for? It's already, yeah, I've already used the constraint in replacing the A with the negative B plus D. So a spanning set for this guy would be what? Yeah. No. So look at W the way we've rewritten it. Do the exact same thing you did in the previous problem, right? So I'd have negative 1, 1, 0, 0. That would be my vector that has the B as the weight. 0, 0, 1, 0. There we go. There's my spanning set for W. Are those vectors linearly independent? Yep, definitely. You could always check by row reducing, but they are linearly independent. So this is my spanning set. It definitely spans W. That's how I came up with the vectors. I was looking for vectors that span W. So I have a spanning set that's linearly independent. So this is a basis. What is the dimension of W? 3. So that means that that space is isomorphic to R3. Isomorphic means two vector spaces that are isomorphic means that there's a one-to-one and onto linear transformation from one vector space to the other. And in practice, it means that those two vector spaces act identically. They're like basically the same. Okay, so here's a matrix A. I want to find a basis for the null space of A. So first we have to remember what the null space is. Yep, the basis is all the set of all zeros that get set of all vectors that get sent to 0. So you augment it with zeros and row reduce, and this will help us develop a basis for the null space. Okay, so 0, 5, 1, 0. That's awesome. Thank you. What do you got? Yeah, so I'm just going to write all out how you get that vector. So this guy's a pivot. This column's a pivot. This column's free. This column's a pivot. This column's a pivot, right? I only have one free variable, x2. So if I were to translate this augmented matrix into a system of equations, this would say x1 plus 4x2 equals 0. And this one would say x3 equals 0 and x4 equals 0. So then what I do is I take each equation that's not explicitly defined and solve it in terms of the free variables. So this guy I would rewrite as x1 is negative 4, x2. And if I were to write this solution in parametric vector form, the vectors form a basis for the null space. Yes, one free variable, so this is one dimension. The null space of A will, its dimension would be 1. So if I just finish out, if I were to put this in parametric vector form, my vector would be negative 4, 0. Yeah, that's a 1 for the x2. Yeah. Negative 4, 1, 0, 0. And if I threw an x2 on there, that would give me exactly this system of equations. Because no, x2 is free. x2 is the free variable, so you need the 1 to keep the x2 free. I should write x2 free over here. So this is my spanning set. This is my basis. Yeah, so the shortcut is just the number of free variables. The dimension in the null space is 1, and you can come up with that by just looking at the number of free variables rather than coming up with the basis. Well, we're talking about the null space of A, not those vectors themselves. But if you just had a set of vectors in the, I don't know what you're asking me. Okay, so a basis for the column space. Well, the column space is just the set of linear combinations of the columns, right? So I would have, just write down the columns. I've got 0, 5, 1, 0, 0, 2, 4, 0. What's, oh, thank you. Thank you. -2, 1, 0, 4. And -5, 14, 2, 10. -5, 14, 2, 10. Okay, so the column space is just all the set of all linear combinations of these guys. So this is a spanning set. It's not necessarily a basis, right? It definitely is a spanning set because the linear combinations of that's the definition of, yeah. So we need to eliminate any unnecessary vectors by taking out ones that are a multiple of another. Right? So we want to keep getting rid of vectors until we're left with a linearly independent set. So this second one is 4 times the first one, so I can get rid of that. Do I have any others that are multiples? Yeah, I don't think so. Yeah. Yep. Okay, so there's my basis. Good. And what's the dimension of this column space then? 3. And what would a shortcut be for coming up with that 3 without actually finding the basis? 4 columns in the matrix minus 1 free variable. Or you could say the pivot columns. The number of pivot columns will tell you the column space. Okay, last one together. I want to find the dimension of the subspace H of P2 that's spanned by these 1, 2, 3, 4 vectors. So P2, isomorphic to R what? 3. So P2, isomorphic to R3. How many vectors are in a basis for R3? 3. Yep. Because it has dimension 3, it's part of its name, right? So it's got to have 3 vectors in its basis, which means that P2 has to have 3 vectors in a basis, right? So both of these would have 3 vectors in their basis. Where was I going with this? I think I'm off track. Right, but this is not supposed to, yeah, this set is not supposed to span P2. It's a spanning set of some subspace of P2. Okay, so this is not going to help me. Sorry. So this set spans some part of P2. Take linear combinations of these guys. You get things that are in P2, but maybe not everything in P2. So how do I, if this is a spanning set, how do I bring it down to a basis? I could turn it into vectors, yeah. So this would be 3, 1, 0, and 0, 2, 1, and 6, 2, 0, and 0, 10, 5. Okay, so I've got it into vectors. How do I decide what vectors to keep, what vectors to get rid of? Okay, yeah, so I have two different approaches. One is inspection. So basically, if this is a spanning set, then I just have to make sure it's linearly independent, right? And they told me that this is the spanning set. Right. So this is a spanning set. Got to make sure it's linearly independent, and linearly independent means no two vectors can be no vector can be a multiple of the others, or no vector can be a linear combination of the others. So we can look by inspection to see if anything's a multiple. Like, so 310, if I scale that by 2, I get 620. So that one is extra, don't need it. Oh, I need one of them, right? So the having the multi, yeah. Yeah, absolutely. We could cross out the first two and keep the second two. But if two vectors are multiples of each other, you get rid of one of them to make sure the set's linearly independent. So I could have a basis of these two or these two, but either way, there are two vectors in my basis, which means the dimension is 2. So the dimension of H here is 2. So we created the linearly independent set by inspection. What could we have done if it was not so obvious? Row reduce, and what would which one do I keep and which one do I throw away? Yeah, keep the pivots, throw out the freeze. Yeah. Row reduce, keep pivot columns only.